this case, this is just a row vector dot product. But in general, Z will be a vector. Thankfully, it's just a scalar. So we're going to need dz dw derivative of this. So dz dw is, we replace with z is w dot t dot x. There's only one w sub k here in this summation, so that means what's left over is just xk. Well, we're going to use a chain rule here. The chain rule says dA dwk is you first take a derivative of a with respect to the argument, and then you take a derivative with respect to the argument with respect to wk. So we've already found out what these two guys are. This guy is that. And this guy is that. Okay, so you just plug these guys in there. And aha. This is our gradient term. How does this differ from your least squares gradient term for a linear model, Abdullah?
We have the residual.
Okay, you have the residual.
In both cases.
What else did you need?
In that case, we have the L transpose. Or X,
elements of the matrix
yeah.
X, except this is a vector X.
Yeah.
But we didn't see this. Where did this come from?
It came from the derivative.
It came from the squashing function. The linear problem, we didn't have a
linear.
squashing function. But now we have the squashing function, and we're going to do an implicit derivative here, or right here. It's going to demand that we take a derivative of the squashing function. Now, normally I put sigma or g for the squashing function, but we're going to have to get used to this a for activation. So we didn't see this before. And this is that bell-shaped curve. So let's rearrange this into something that we're very familiar with, x transpose times the residual, and this is the something new part. And if you want to include the I in our previous example of the motorcycle, we had a lot of motorcycle runs. In each run, we did a vector row vector dot product, and therefore you could denote the elements of that matrix X by xik. So I would be each new experiment. So that gives you a clear one-to-one mapping from what we did before, what we're doing now, except we have this new. Okay. Can I go on, Abdullah?
No, fine.
Abdullah, I'll be asking permission if I should go on or should stay for you guys to think about this. So if you can't understand my lecture, you can go.
Are you guys okay?
What? And if I'm speaking too fast, someone say something. So here's our friend. Abdullah just derived this. And that's, of course, the gradient. And steepest descent then is bingo. Yeah, let's take that and write a code. And Abdullah's great at writing code now. So what I did was I collected all my x's into a big matrix. Oh yes, what should I write? Okay, here are my x's. What does each row physically correspond to, Abdullah?
The intensity of pixels, or
One photograph or 20 photographs?
each row. It should be one photograph.
Oh, one photo.
Yeah.
Okay. One example. One experiment. Okay. By the way, if any of you have pictures of your own motorcycles or your scooters, in the case of Luca, he has a little Vespa problem. It's really interesting seeing him, a 6'5" guy on a Vespa running around. Right?
I have a chow.
What?
I have a chow.
What?
The one with the pedals. It's very old Italian. I don't know. It's the one with the pedals.
You mean a bicycle?
Oh,
Yeah, motorbike.
Oh, that doesn't. Oh, okay.
From the
Okay.
70s.
Anyway, send them to me and we can put them into the, so we can start backing up some of the information here. So we have these, so each of these is a row, so you can think of this as a giant matrix, X, that contains all of the examples, all of our inputs. So I'm going to extract one of these guys. You know what MATLAB, how MATLAB works. One of these guys I'm going to call X. I'm going to grab for this row, I'm just going to grab everything along one row and call it little x. And then I'm going to take my w and do a dot multiply it by the x, assuming things are right dimensions. And that's almost my predicted class, but not quite. What do I have to do to make this a prediction, Abdullah?
You need to take the activation for it and see if it's 0 or 1.
Get it like a squashing function.
Yeah.
Okay. And here's my squashing function. So A1, this is MATLAB. So I just take this guy and put him there, and now that's my prediction. Okay.
So A should be 1.
Oh yeah, it should be a
yeah.
plus. Who said that? Sharon. Very good. Thank you. So now we take a residual, because that's what we're going to demand over here, right here. So our residual is going to be the prediction of the class minus the actual t, and I guess you'll just have to believe me. I extracted the t associated with this class, the observed t. And what I'm doing here is now I'm doing what am I doing here? Abdullah.
Where?
This guy. Here's my residual.
The residual. Here you're
What's going on here?
You're computing the gradient and updating the model.
So I'm updating the W for all the photographs or just one photograph?
For 1 up to K. It's for one photograph. Let me see. Yeah, this one for one photograph.
One photograph.
Yeah.
This is called the stochastic gradient method. I don't like it.
It takes time.
No. It doesn't take time. I don't think it goes anywhere. That's like if you're doing least squares migration FWI, you convert one shot gather at a time. And so the model you get to explain that one shot gather may be inconsistent with the model you need to explain shot gather number 2, and vice versa, And then they take the new model, W, then they go back and feed another photograph in there and then update the W for that and hope for the best. That's a crazy thing. The better way to do it, oh yeah, this is when you get really lazy.
Okay.
Well, yeah, no subroutine, just it works sometimes. It's called stochastic gradient, but the one I prefer, and I think most of the community prefers, is a batch gradient, where you iterate over batches of photos at a time. So what that means is you would find that you'd have another where would you put the do loop for the photograph markup? If you want to start finding the gradient for all the photographs, or a batch of them, where would you put a loop over different photographs?
Should be like before, inside between K and
Yeah, you do something in here
yes,
where you would
by the
find
matrix and
the gradient for each photograph and add it on to one
But
another.
it's more a matrix than
What?
it's more vectorized computation than a cycle.
Yeah, I'm doing a very explicit notation, not vectorizing things.
4QU replace the X with the full XX.
Yes.
Or
Yeah,
sub matrix or not.
Yeah, you would do something like this. You would, and then you kind of have a loop. And then I take this whole piece right here and I take this piece and put it right in. To get the gradient for each photograph, then I'd add each gradient to one another. At one iteration. If I had 10 photographs, I'd have 10 mini gradients, and I just add them together to get a super gradient, a composite gradient. And then I'd move in that direction, and I'd see if all those photographs were explained. Piece of that, repeat that, repeat that. Okay. Cross entropy. That's all of that. Now, I think Abdul is kind of he has some experience with inversion. Maybe some of you, and I think you probably do. What is your name?
Chow.
What?
Chow.
Chow? Okay, Chow has probably more experience with inversion than those folks do. When you come up with, say, residuals, Chow, the residuals are vectors. You're summing up all the residuals. Are there rules of thumb for what kind of misfit function? I mean, that you can't use? I mean, is it okay to do something like this? Is anybody stopping you? Is there any natural law stopping you from that? Check. Yes or no? You have to think outside the box. Check.
I don't think
No.
it's limit. No limit.
What if you did something like this? Log. As long as this guy did something like this, took a log of that, this is a monotonic function. So the log, what a log does, it takes numbers over a large range and squashes it down over a small range. For example, log of 10 to the, well, let's call this what is that? Chow.
5.
And what's the log of 10 to the 10? Chow.
1.
So, 5 orders of magnitude difference between the input, between the input 10 and 10 to the 5th. But after you do a log on it, just squashes that down to a much smaller range of numbers, right?
Yes.
Chow. Okay. So, and the reason we can do, is this okay to have as a misfit function, Chow?
Yeah, I think so.
Why not? Well, the reason is, this is a monotonic, if you have a monotonically increasing function here, or it could be decreasing, this will follow the same ups and downs as this, except at a much reduced slope. So if this is increasing, the log of that will be increasing. Okay? If this is decreasing, this will be decreasing as this gets decreasing. And if this has a global minimum, say right here, will this have the same global minimum? Chow.
Yes.
Okay. So there are really no rules as to what kind of a misfit function you can cook up as long as it has a behavior that's desirable. And that's what the cross entropy can be explained in that fashion without any use of probability. But I'm going to break my vow of probability silence and talk to cross entropy in terms of probabilities. Okay. So, conditional probability function is going to be binary. What does that mean?
It's either 1 or 0.
One thing or the other. It's like a coin flip, heads or tails. And so they denote conditional probability in this fashion, and X and Y are random variables. And what's a random variable? I'm going to ask our resident mathematician.
It is a random variable.
What's a random variable?
It's a probabilistic. Is a
No.
variable.
You can't use the word probability.
It's a
Use
variable.
human language.
It's a variable that can take different values depending on the underlying distribution.
It's a variable that can take on different values. You know, function can take on different values.
No, but it's there's no deterministic. It's not a
Yeah,
deterministic
you can't
function.
predict what that variable is going to be at any one time or place.
Yeah.
It's not a deterministic
It's
function.
not deterministic.
At noon, if I have a random variable x at noon,